Okay, our example number 1. Calculate the power rating of 180% efficiency of the pump needed to deliver water at the rate of 10 liters per second from reservoir A to reservoir B. Inlet pipes and outlet pipes are projecting. Pipes are HGI. Assume water in the pipe is at 20 degrees Celsius. Then sketch the energy grade line and the hydraulic grade line. So, you have to first analyze, or you have to be careful what power you need to determine, if it is power output or if it is power input. Then second, you have to know how to illustrate this problem, because I will not give illustrations, and you have to also understand every word of the problem. So here, our outlet pipes are projecting, so you have to determine if the outlet or inlet pipes are projecting or not, or if the inlet pipes will be flushed at the entrance, or the outlet pipe is free or at free fall. So you have to understand. Then pipes are all GI, so this is galvanized iron, so it denotes the type of material you are going to use, because we need to identify what type of the materials, because we have to get the relative roughness, because we have to use it depends on how we are what formula we are going to use for our head loss. If we use the Darcy-Weisbach equation, if we use the Manning's equation, if we use Hazen-Williams. So sa Darcy, you need to find the friction factor. For the Manning's equation, you need to use the roughness coefficient of the pipe, and for the Hazen-Williams, you need the C. So I hope you know all of these things, because I include this in the lecture videos, my previous lecture videos. Okay, then we have to assume the water in the pipe at 20 degrees Celsius. So we need to determine also the temperature of the water, because it also gives us, or from the temperature, we will know the properties of the fluid, or the properties of the water that we are going to use. So this data are also tabulated. Okay, so if you have a fluid mechanics book, so you can refer at the back of the book, or any fluid mechanics book, you can have the list of the properties of fluid at different temperature. Then you have to sketch the energy grade line and the hydraulic grade line. Okay, so first we have to illustrate the problem. So here, okay, you have reservoir A. Okay, you have reservoir A. Then it is said that the inlet pipes and outlet pipes are projecting. So this is very important information, because it depends on the calculation of our head losses at the inlet pipe. So this will be the water surface of the reservoir A. The elevation here is 30. Okay, so 30 meters. Then so if if there's no illustrations, no, if there's no illustrations given, so the illustration will be described, no, in the problem, the situation will be described in the problem. So if it is not described in the problem, so the illustrations will be given. So here you have the pipe, projecting pipe. Then you have pump, because as what I've said, you need pump to add the head in order you can deliver water from lower elevation to higher elevations. Then we have also another pipe which is also projecting, and this pipe will deliver water from reservoir A, okay, to reservoir B, and the elevation of this one is 40 meters. Okay, so for the actual situation, you can think that reservoir A will be the source, no? So reservoir A will be the river, no? Okay, you have to take water from the river, then that will be your reservoir A. Then you have to pump water and deliver it to a large storage tank or large reservoir, and that will be your reservoir B, and the location of your reservoir B is at the highest elevation. So we also have here, I put, no, we have there the gate valve. So for example, we have here gate valve, then you also have there check valve. So that's it, no? Then we need also to have the length of each pipe. So we have here, okay, you have 20 meters, then you have 10 meters, then another 10 meters, then you also have another 40 meters. So it is assumed, no, the length of the pipe is 40 meters from, okay, for the total length, no, we're just assuming the length of the pipe. So we have 20, 30, 40, so 80, right? So 80 meters. Then we need also to determine the diameter. So here we have to put 10 mm diameter for the suction pipe. Then you have 150. So we assume, no, if you have 150, okay, 150 mm. Okay, so we have now our figure. So first you have to list down what you are going to find. So we are going to find the power rating of the pump. So we have the power rating of the pump. Then that will be bit number 1. Then we have to sketch the HGL and HGL. Then after that, you have to list also what are the given. Okay, for the given, we know that the type of the material is GI pipe. So from that information, okay, GI pipes, we can get the, okay, we have to refer from table what is the relative roughness of a GI pipe, because we need the relative roughness to get the friction factor. The friction factor is used if we in determining the head loss of the pipe, we can use the Darcy-Weisbach equation. Okay, so that is from the table, that is A is equal to 0.15. Then at 20 degrees Celsius, okay, your the properties of the fluid, no? Because we need also to determine the Reynolds number, no? For the friction factor, there, Goldbrook-White equation, that is for turbulent. If we found out if the flow is turbulent, we have the friction formula of the friction factor, and we determine it by getting the Reynolds number. So from the Reynolds number, you also need to have a dynamic viscosity and kinematic viscosity rather. But from that, we need to identify the temperature of the water. So you have there dynamic at 20 degrees Celsius, you have 1.002 times 10 to the third, okay, per meter square. That is Pascal second or Newton second per meter squared Pascal. And the kinematic viscosity is 1.003 times 10 to the negative 6. This is negative 6 meter squared per second. Then Q is equal to 600. Okay, you have 100 liters per second, and this will be, we have to convert this into cubic meter per second so that we can cancel out all the units. So these are the given. Okay, next we'll have to determine the friction factor of our pipes. Okay, let's say this is our pipe 1 and this will be our pipe 2. So pipe 1 have a diameter of 100. Okay, 100 mm. Sorry, this is 100 mm. Okay, you have 100 mm. And pipe 2, you have 150. So you have 150 mm. So we have to write, okay, for small pipe, and that is our pipe 1, which have a pipe 1 has a diameter of 100 mm. So convert this into meters. So we have 0.1 meters. Then the area of pipe 1 is equal to pipe over 4 d1 squared. Why? Because we assume that the pipe is flowing full. So this is the cross section of your pipe. So it is flowing full. So the area of flow, okay, the area of flow is just equal to the diameter of a circle. So we have to substitute these values. So we have pi over 4 times 0.10 squared. So this is equal to 0.01 pi over 4. Then we have here our velocity. Velocity is equal to Q over area 1. The Q of your problem, the discharge of your problem is constant. Okay? The entire flow of the water in your problem is constant. So we have Q which is equal to 0.01 over 0.01 pi over 4. So this is equal to, okay, you have cancel, so you have 4 over pi meter per second. The next is the Reynolds number. Okay, we have the Reynolds number. We have two formula for the Reynolds number. You can use the Reynolds number using kinematic equation, or Reynolds number using dynamic equation. So if I use kinematic equation for getting my Reynolds number, so this will be my formula. So D1 V1 over kinematic. So you have 0.01. Okay, so 0.1 times 4 over pi divided by 1.003 times 10 to the negative 6. And that is equal to 1.27 times 10 to the fifth. Okay, to the fifth. So this is greater than 2000. So we can use the formula of Colebrook-White equation in getting the friction factor. So this is greater than 2000. Okay, so when you say 1.27 exponent to the 5, and that is equal to 127,000, and that is greater than 2000. So the flow here is turbulent. So we can have also this one, the relative roughness, 0.5 over 100. This is 0.0015. Okay, so we already have our data in getting the friction factor. So in getting the friction factor, you can use Modi equation. So F1, or from the chart, which is from the Modi diagram, your F1 is equal to 0.023. Or by using Colebrook-White equation, you can also get F1 is equal to 0.023. So you have the option. So for the Colebrook-White equation, you can get directly or you can get the friction factor. If we use Colebrook-White equation, we have this formula. Okay, you have 1 square root of f negative 2 log E over D divided by 3.7 plus 2.51 NR square root of F. So by calculating the friction factor using Colebrook-White equation, you can have the same results from the Modi diagram. So F is also equal to 0.023. Okay. Next, we have also to get the Reynolds factor. The friction factor for the larger pipe. So for the larger pipe, D1 is equal to D2 is equal to 150 mm, which is 0.15 meters. A2, you have pi over 4, D2 squared is also equal to pi over 4 times 0.15 squared, and this is equal to 0.0225 pi over 4. Then V2 is equal to Q over A2. This is 0.01 divided by 0.0225 pi over 4, which is 0.566 meter per second. Okay, per second. So every parameter we have to round off our value up to 0.3 decimal places. Then Reynolds number. Okay, you have 0.15 times 0.566 divided by 1.003 times 10 to the negative 6. So this is equal to 8.463 times 10 to the 4. So this will be 84,000. So okay, 8.463 exponent to the 4, this is 84,630, and that is greater than 2,000. So it is turbulent flow. Still, we can use the equation of Colebrook-White in getting the friction factor. So 0.0, so the relative roughness is equal to 0.001. Okay, then we can have, okay, from Moody diagram, your F2 is equal to 0.0226. So this is round off or taken at least 3 significant numbers. So same Colebrook-White equation, using Colebrook-White equation, your F also 0.0226. So you have to round off or get the friction factor up to 3 significant numbers. If it will start from 0, so we have to use 3 significant numbers. Okay, then we have to get or use energy equation of from reservoir A to reservoir B. So okay, you have to write the energy equation. Okay, the energy equation. Okay, energy equation from reservoir A to reservoir B. So we have there P over gamma. Okay, PA over gamma plus ZA plus V squared over 2G plus head of the pump, because we have there the present of the pump. Then P gamma plus CB plus VB squared over 2G K plus summation of head loss from reservoir A to B. So since both are exposed to atmospheric pressure, so you can write, because we start from reservoir A, it is exposed to atmospheric pressure. Then B, it is also exposed to atmospheric pressure. Then we have now to write, since the elevation at A is 30, okay, plus, okay, supposed to be, we have there the velocity head, but the velocity head at reservoir A and B are considered negligible, because compare it to the pipe, it is negligible, no? The velocity in the pipe is lesser than the velocity of the two reservoirs, so we can neglect it. Then we have here HP, so we have also 40 for the elevation of reservoir B, and that is equal to summation of head loss. So we have now our equation for head of the pump, that is equal to 10 plus summation of head loss. Okay, so for the head loss, we have 2 types. Now we have to add all the head losses. So we have 2 types of head losses. We have minor losses and the major losses. So we have the head loss for minor and the head loss. Okay, head loss for minor and head loss for major losses. So for minor losses, we have to check what are the minor losses, and for the head loss, for the major losses, these are the head loss of the pipes due to frictions. For minor losses, these are the losses due to the loss at the entrance, loss at the discharge part, loss due to fittings, pipe fittings. If there is also bending of the pipe, so those also comprises the minor losses. So we have to check, no, in the problem. So from the problem, we only have head loss at the entrance, plus head loss. Okay, we have to check head loss of the gate valve, head loss of the gate valve, plus head loss, okay, head loss of the check valve, and head loss of the discharge, plus the major losses. You have head loss of pipe 1 plus head loss of pipe 2. Okay, where we have to solve one by one. So we have here for the head loss at the entrance, so that's why we have to check what type is the entrance of the reservoir. So from here, it is projecting, so KE will have 0.80. So here, head loss of the valve, so we have to take the head losses of the fittings and the valve from the table. So we have 10, then head loss. So this is a check valve. So we have squared. So you have to review again the notes, the lecture notes na akong. The lecture notes, I give it to you, okay? So KC over 5, then HD is equal to, the discharge is submerged, so the coefficient of discharge is also equal to 1. So KD is equal to 1. So then we have HF1 because we use Darcy, so you have FL1 V1 squared over D1 2G, then HF2 F2 L2 V2 squared over D2 2G, right? Then we have to substitute. Okay, so after that we have to compute. So the head at the entrance is 0.80, okay, 4 over pi squared. So this is equal to 0.066 meters. Then HB, you have 0.10. Okay, you have 4 over pi squared. So, okay, divided by 2G. So you have 0.826 meters. Then we have HC, so we have 5, okay, times 0.566. Okay, I have to, okay, squared over 2G. That is, G is 9.81. So I have to Okay, this is 2 times 9.81. This is 0.066 meters. I have to emphasize G. This is 2G, and that is 9.81. Okay, that is 9.81. So this is 0.082 meters. Okay, then again, for the head loss at the discharge of 1.0 times 0.566 squared over 2 times 9.81. This is 0.016 meters. Then you have HF1, you have 0.023, okay, times 30 FL, okay, times FLV squared. So you have 4 over pi squared. D, that is 0.1 times 2 times 9.81. So you have 0. Okay, you have 0.57. Then you have HF2, you have 0.0226. Okay, 50 times 0.566 squared over D2G. So this is equal to 123 meters. Okay, so we already computed all the head losses. So we are ready to, okay, we have to make this our equation 1. This one will be equation 1. So we can say from equation 1, okay, from equation 1, HP is equal, this is the head of the pump. This is equal to 10 plus 1.683 plus, okay, sorry. Okay, we have to, okay, 10. So if we have to sum, sorry, if we have to, okay, 1.83. Okay, 1.683, this is equal to 11.683 meters. So here, I directly add all the head losses, and that is equal to 1.683 plus 10, that is from equation 1. So the total of the head of the pump is equal to 11.683. Okay, because we need to determine the power, okay, the power of the pump. So the power of the pump, so it means that is the power output, okay, because the power input of the pump is the electricity. Okay, so the power here, correction, the power here of the pump that we need to get is the power input. Okay, the power input, because the efficiency is also given. So the efficiency is also given, which is 80%. So we have to add also here for the efficiency, which is 80%. I have to write now efficiency of pump, which is equal to 80%. So here, the power we need to get is the power input. Okay? Because we need the power input or the power input of the pump in order to add the head of the flow energy to deliver water from 30 from 30 meters, that from 30 meters to 40 meters, from 30 meters to 40 meters. So we only here for the flow energy, what we get is the power output, because this is the flow energy that we can get using the pipe. So we have Q HP, that is the flow energy, and that is 9.81 times, we have to convert 9,810, that will be in Newton per cubic meter, times 0.10, 0.01. We'll check for the Q is 0.01 cubic meter per second. So 9810.01 times 11.683, and this will be equal to 1146. 11 again, I have to check again. 9810 times 0.01 times 11.683, so 1146.1023.102. So this will be Newton meter per second, and this is also equivalent to 1146.102 watts. Okay, so to convert this into horsepower, so you have power output, that is, you divide it by 746. Divided by 746, you have 1.536 equals to 1.536 HP. So that is not the head of the pump, that is the horsepower. So I have to put horsepower. Maybe you can say that is head of the pump. Then we have now our power input. So this will be your answer. Power input PI, and that is equal to 1.536 divided by 0.8. That is 80%. So therefore, power input, that is the power of the pump needed, is equal to 0.8, sorry, 1.536 divided 0.8, and that is 1.92. 1.92 HP. So that is horsepower. So maybe you can say also HP. So this will be horsepower. So this is your answer for number 1. Okay, this is what I need you to give to me. Okay, this is what I need. This is the answer for question number 1. Okay. Okay, for the sketch of the energy grid line and hydraulic grid line, I have to copy the figure. Okay, I need to copy this one. Okay, copy. Okay, so this is the figure. So I have to erase this one. Okay, I have to erase. Okay, then I need to draw a vertical line as my reference point. This one I have to draw, and this one. Okay, so for the energy grade line and the hydraulic grade line, first I have to sketch the energy grade line, because energy grade line, or the point of every point, or the total head of every point, is just equal to the total head minus the head losses at that point. So for example, at the entrance, so for example, from here to at the entrance, like this, so we need to get the head, no? For example, at this one, so we know that the entrance, you have there the losses, so we have 30, that is the total head, no, at that point. So if you do or write the energy equation from here, so we have this one as our from the water surface to the entrance. So you know there is a head loss at the entrance. So the head loss at the entrance is 0.066. So it's just equal to 30 minus 0.066. So 0.066, where I get the 0.066, that is the head of the entrance. Sorry, the head loss at the entrance. So that is, okay, you have 30 minus 0.066, so you have 29. So you have 29.934. So this is 29.934. Okay, this is my point. Then again, write the energy equation from this point at the entrance to the location of your valve. But before that, we have there the head loss due to your friction. Okay, that is the head loss due to friction of the pipe. So we have to subtract 29.934 from the head loss of pipe 1. So the head loss of pipe 1, we don't have yet the head loss of pipe 1. So we can get the head loss of pipe 1 because the length of the pipe 1 is before the valve is only 20. Okay, before the valve you only have 20. Okay, 20 meters. So if we get there, so here we use 30, that is the total friction loss of the pipe. So if we have the 20, if we try to get what is the head loss for 20 meters and what will be the head loss of 10 meters, so we have to change this into 20, no? So in that case, for 20, you have to compute the head loss, or just put a ratio and proportion because it is just equal. So when the pipe has the length of 30, the head loss is 0.571. So what will be the head loss if your pipe is 20? Okay, so this will be your x1. So I'm just using that equation, or you can use it by substituting, no? You can use it, getting the head loss at 20% by writing all the formula and change the 30 to 20 or 10 or any length. So you can determine the head losses. Okay, so for my equation, 20 times 0.571 divided by 30. So my head loss is 0.381. So I have here 0.381. For 10, so how about if I have 10? 30, 0.571, and if it is 10, that will be your x2. So at x2, what will be the pipe loss? So you have here 0.90, so 0.19. Okay, so 0.19. It should be, if you add 0.19 plus 0.38, it should 0.381. It should have a total of 0.57, no? Because that is the total head loss of the pipe having a length of 30 meters. So same also for the HF2. So maybe you can also have, when the pipe is 50, your head loss is 1, 2, 3. What will be the head loss if it is also 10? 10 times x, we let this one as x3. So x3 is equal to 50. Okay, 10 times 0.123 divided by 50. So you have 0.025, 0.0246. Then we have x4 again. So I have to, okay, for the x4, okay, so how about for the x4? You have 50 over 0.123, which is 40 over x4. So we have x4, that is for larger pipe, 123 times 40 divided by 50. So you have 0.984. So 0.9, 0.0, okay, 0.0984. So you have to add 0.0246. It should have a total of 0.123. So which is correct. Okay. So we have to do this because for the sketching. So here again, we have to compute again. So the head loss for friction 1, or for the head loss of pipe 1, is equal to, you have to minus, that is, the head loss is 0.381. So minus 0.381. So that is 29.553. So this will be 29.553. So this is not scale. So I hope you can follow. This is not scaled sketch. So 29.553. Next is for the valve. So for the gate valve, this is very close, no? So for the gate valve, how can I make this into bigger? For the gate valve, your valve for the gate, for the head loss of the gate valve, you have 0.826. So minus 0.826, so you have 28.727. So this is very close. So 28.727. Okay, maybe I have to draw again, no? To redraw my vertical line. Okay, so I have to draw like this so that you can see it clearly. Okay, so this will be, so this will be my 28.727. Okay, then again we have also the head loss due to pipe friction. That will be our x2, 0.90. So that is 0.19. So you have 28.537. Okay, so we have here, so I have to zoom, so maybe they are 28.537. Anyway, it's as long as you have the elevations. Then next is pump. we have the head of the pump. So we have to add because it is pump. That is the head added. So plus 11.683. So 28. Okay. So we have here 28.537 plus head of the pump, which is equal to again, what is that? Is 11.683. So we have here the pump, that is the head of the pump. So we have 40. So we have here 40. So 40.22. Okay, so again we have here the pipe friction. So I need to redraw again the vertical line. So I hope you can follow. That's it. So 40.22. Okay, the friction of the pipe is 3.0246. So that is 40.195. 40.195. So here 40.195. This is exaggerated, huh? This is an exaggerated elevations. So this is 40.195. So 1954 supposed to be. So I have to carry all the decimal places. Then again, for the gate valve, a check valve. For the check valve, you have 0.082. So check valve. So 0.80. Okay, minus 0.082. So you have 40.1134. Okay, you have 40.1134. Okay, you have 40.1134. Then again, we have again head loss due to your pipe frictions. Okay, pipe friction, that we denote it as X4, and that is 0.0984. So that is 40.015. Okay, so we have here 40.195. So 40.015 again, sorry, 0.015. Then we also have the head loss at the discharge. Okay, 0.016. So we have a small error for this. So when we have minus 40 point, okay, 0.016. So the error is 0.001, or more or less that is equal to 40. Okay, so 40, which is, we can check that that is correct because the elevation there is also 40 meters. So we can say that our computation for the energy equation is is correct, no? Then we have to sketch. Okay, we sketch, which we will connect all the points. Then here we will connect all the points. Okay, what happened? Okay, we have to wait. What happened to the... Okay, we have to... Okay, what happened? Okay, where is my problem? Okay, we have to connect again. Okay, we have to connect. Then... Okay. Again. Okay, we have to wait again. I don't know what is happening. Okay, then we cannot eat it. Okay. Okay, we have to connect again. Okay, so we have here, then we have here and here. Okay, so this is my energy grade line, the blue. Okay, the blue. Okay, this is our legend, no? The blue is energy grade line. So legend, I'm just use the legend. And maybe for the, okay, I have to choose black, I guess, for my hydraulic grade line. So for the hydraulic grade line, that is just the difference, no, of the total head and velocity head, no. No, sorry, the difference of the energy grade line and the hydraulic grade line is equal to the velocity head. Okay, so when you say the hydraulic grade line, that is equal to elevation head plus the pressure head. When you say the total or the energy grade, the energy head, no, when you say, because the line is just the points connect, it is the line connecting all the head, no. So it's just the difference of the difference of the energy grade line and the hydraulic grade line is equal to the velocity head. So we have to check, no. So here we have okay, v1 squared. So v1 squared over 2g. Then we have also that is equal to, and we also have v2 squared over 2g. So for v1, what is the v1 here? The velocity. Okay, so where is the velocity? Okay, velocity v1 is 4 over pi 0.566. Okay, 4 over pi 4 over pi, sorry. Okay, 4 over pi divided by 2g, and this is 0.566. Okay, this is squared over 2g. This is squared. So I have to transfer this. So we have, this is equal to, so you have 4 over pi squared by 2 divided by 9.81. So this is point, okay, this is 0.826 meters. And 0.566 squared divided by 2, 0.81. So this is 0.0163. Okay, so here, so you just get the difference. So 29.934 minus 0.0826. So you have 29 point. So I have to write here, okay, 29.851. So 29.851. Okay, I hope you can see it. Then here, 29.553 minus 0.0826. So you have 29,800. So here you can write 29. So here, maybe you can have, okay, 29.8. So this is your application of your energy, of your hydraulic grade line. So you have 28.727 minus, again, 0.0826. So 28,644. So here you have 28. So 28.644. Okay, then 40.1954 minus, that is for velocity 2.0163. 40.1954. Okay, 40.179. Okay, 40.1954 minus 0.0163. So you have 40.179. The same. I guess I put the wrong number, 0163, 40.023. So this is 40.24. Then 40.1134 minus 0.0163, you have 40.097. This is 40.097. Then 40.015 minus 0.0163, so that is 39.998. So this is, okay, 40.015 minus 0.0163, so that is 39 point. So you have, okay, so that is equal to 40. We have to round off, so we have to connect this line, then again connect that line, then, okay, so that will be my, okay, this will be, I need to connect, okay, I missed something, 0.727 minus 0.0826, 20.644, so this is 28.644. So, okay, then, okay, so this is my answer for the sketch of my hydraulic grade line. So I hope you understand and you can rewrite all of this, no, in your notes. Thank you.